Okay, welcome. Today we're going to talk about convolution. To begin with, let me just emphasize what have we done so far in the class and how what we're going to do now is a little bit different. So far in the class we've learned about the Fourier transform, and in your lab beginning this week, you've actually used that to begin building Shazam, right? Shazam is a great example of analyzing signals using these tools that we've learned, the Fourier transform in particular, the short-time Fourier transform. And that's one use of these tools. Another use is to actually change the signal, to do a manipulation to your signal. Okay? And that's what we're going to begin talking about now. That's what convolution is a great example of. And we're going to want to understand what's going to happen to a signal when we make certain manipulations to it. Think of this as an example that's here is one where you might want to do some smoothing of a signal. So imagine, this picture of the eye here is a two-dimensional signal. The domain is two-dimensional. Everything we've talked about in class has pretty much been one-dimensional signals, and we'll continue to do that. But all of the techniques and mathematics we learn will easily generalize to higher dimensions like images. Okay, I'll let you use your creativity to connect those, and you'll do that in the labs as well. But this is just a signal where this is a halftone image. So you see that to make darker shades, they have circles of black that are of varying sizes, right? And that's how this is made. This is a technique often used in printing newspapers, for example. So if you think of this is a signal where the value is white, or it's some level of gray. And if you'd like to imagine this signal, since we're used to plotting things where the value takes on a vertical representation, think of this as a contour, and white is how high is the elevation. All right. So as you'd notice, if you were to walk around this space, there would be a lot of bumps, right? You'd walk from low spots to high spots. It's very peaky. That's because of these blops of black and white everywhere. Now, you can do what's called a low-pass filter to remove high-frequency bumps like that. One way to do that is doing a local smoothing. All right, and so down below is just a smoothed version of the above one. Where for each point, and we saw an example of this in a previous lecture, for each point, an average of local values is taken, and then that the output image has that average value rather than. So in other words, to calculate the grayscale value for a particular point in this resulting image, you just take the input image and average around that pixel to calculate that value. Okay, so it's a local averaging. So that, in fact, is convolution. So let's discuss this mathematical operation that we call convolution. So mathematically, we would say that we write x of n, two signals are convolved, and we use this asterisk to represent that. X convolved with another signal we'll call h of n. And the formula to calculate the output signal is this infinite sum. Okay, so it's pretty straightforward. Now let's talk about what this means. First of all, let me mention this is discrete time convolution. And continuous time will be similar, but we'll actually wait to discuss continuous time convolution until the next lecture. Okay. So this is discrete time convolution. What it is, it takes two input signals, two signals in, and it gives us back, this is one signal. Why do I say this is one signal? It's a function of n still. So the convolution of two signals is not just a number or some complex number. It's an entire new sequence, right? An entire new signal. So I should emphasize that n here is the resulting variable, because we're summing over k. Whoops. Okay, so the result of this will be a value for each n. So it's a signal. Okay. Let's do an example, and then we'll just really become familiar with this. Okay, so suppose you've got an xn like the following. So let this be xn, okay? And it's 0 everywhere except on these three values. All right. And similarly, let's define an h as an example. All right, and this one is going to be one, 2, 2, 2, 2, 1. Okay, and 0 everywhere else. Now we want to discuss the convolution between these. So here's our h of n. Okay, so we need to calculate an output of this convolution, which itself is going to be an entire signal. So what we're going to do is calculate it. In this example, we're going to calculate for each n individually. So the technique is this. We need to do this sum. So this technique people refer to as the flip and shift technique for calculating a convolution. Okay. Notice that we can draw these lined up because we're going to do a sum over all k. So what we can do is let's now have k be our axis for this sum. Notice it's a sum over k. So of course x of k is exactly x of n, but I'll just redraw it here so we can line things up. 0. Okay, there's x of n. And let's look at what does, let's draw h of negative k. Why are we doing that? Because you'll notice in this sum, what we actually need to sum is h of n minus k. Okay, I'm going to represent h of n minus k will be convenient. For the sake of thinking this as a flip and shift, think of h of n minus k equals h of negative k minus n. Okay, of course that's equal. But think of it that way because k, we're plotting with respect to k. We're used to seeing things written this way. And we can see that this is the negative 1 flips things in time, and the minus n will give us a shift. Okay, so in other words, we want to look at something like h of negative k, which is just going backwards. All right, that's h of negative k. And so this will be the calculation for n equals 0. What we'll do is we'll multiply these two and add them up, right? So the output. So when we multiply these, there's only one overlap here, a 1 times a 1. Everything else is a 0 times a number, right? So we end up with 1 is the value. Okay. Now for n equals, let's do the calculation for n equals 1. What we need to do here is plot h of negative k minus n, which is 1, right? All right. So this is going to be, you shift it, rather than be at 0, everything's going to shift to the right by 1. And these are all 0. Okay, now again, we're multiplying this h of this function by x of k. Now there are two places where they with non-zero overlap, right? So we do the multiplication. We get a 2 times a 1 plus a 1 times a 2. All right, so we get 4. See how that calculation is done? The only thing I'm skipping is drawing what the product of these two is. I guess you could draw it in another color here. I could say, the product in this case was just 1, 0, 0, 0, 0, 0, right? That's the product of these, of xk with this function. Product of xk with this one is 2, 2, 0, 0, 0. Okay, and the convolution formula says you should then sum that up. All right, so we get 1, we get 4. Let's go ahead and n equals 2. Of course, you can see that you're going to get a 1, 2, 2, overlap, and then this part doesn't overlap. So this is, these first parts are the parts that overlap. The product is going to be 3 times 1, so that's 3, 2 times 2, 4, 1 times 2, that's 2, 0 everywhere else. Okay, so we get 9. All right. Now this isn't going to go on forever because I picked a signal that was easy and that ended up having zeros. So we could keep doing this. N equals 3. We'll get okay, we get 0 here, and we get 6, 4, 2, and then zeros. So 12. All right, now it's going to start going away once we do n equals 4, shift by 4. Okay, and the overlap, we can't see our function anymore up there. So we get a 1, and then we get a 2 times, we get a 4. I'm not gonna plot it anymore. I'll say it's a 1, a 4, and a 2 times a 3, 6. So that's 11. Output n equals 5. I'm no longer going to draw for the sake of time. So we're going to get a 2 plus a 6. Right? Whoops. 2 and a 6. So this output is going to be 8. And n equals 6. We're going to get a 3, and that's all. The only overlap will be, I think you get the idea, even though I stopped drawing things. So it'll be 3, and then for n equals 7, let's actually draw this out. N equals 7, here's k. You actually now go up to, so there's 0, 1, 2, 4, 5, 6, 7, and it's like this. So that is h of minus k minus 7. Okay, and notice that there's no overlap now with x of k, so the product is just 0. And it's 0 for the remainder. Anything greater than 7. You see this? Have we finished calculating the convolution? We've calculated its value for all these points. And anything greater than 7. Have we finished? There's something we forgot. We need to know negative ends as well. It's not sufficient just to look at positive ends. A signal goes from n equals negative infinity to infinity. We started at 0. What? Okay, so if we shift back the other way, notice that for n equals negative 1, this is going to shift to the left, and there will be no overlap for any shifts to the left, just for this particular signal. But in general, you have to check. There might be some overlap. Okay? You have to go both ways. So for this example, negative ends were all 0 in the output. So if we say that y of n equals the convolution of xn and hn, then what we have here is that here's y of n. 0, let's see, we have values all the way up to 7. Actually up to 6, and then we have a bunch of zeros. So the function that we got, it's hard to fit it all in one screen, 1, 4, 9, 12. So we have something like this. 1, 4, 9, 12, and then we could have 11, and then we have 8, and then we have 3, and then we're down to zeros. And we were zeros over here too. So that is the output signal. Okay, that's the convolution of these two inputs. Again, we have a plot of the inputs, so let me scroll up to see it. So when you convolved this signal with this signal, you get this thing. Okay, I could put the lines to make it similar here. Okay, you get this. It's your output. All right, so some things to notice. First of all, you can think of this h. You can think of this as being a weighted average of x. Let's say x is some input signal, and we're doing a weighted average defined by h. Why would I call this a weighted average? Well, because notice this is your weighted average function right here. This is your weighting function. It says for each output value, I'm going to use this, you might call it a kernel or something. I'm going to use this weighting to decide how much to weight the inputs. You know, add them up according to these weights, and that will be my output. Now, if you usually you think of averages as truly being an average where these weights should sum to 1. Fine, I can pick an h where all the values sum to 1. All right, and then it would be more like a weighted average you're probably used to. But anyway, what I'm doing is I'm taking some weighting of the input signal centered around a point in time. And then I'm outputting that value at that point in time. And then to calculate the next output, I'm just shifting my weighted function. That's exactly what we talked about before by doing a local weighting. All right, so convolution is a local weighting. You might find it kind of odd that instead of defining the weight function explicitly, we define some h where h of negative, the time shift, is the weights. Okay. So h is one of the is specified in the convolution formula, and it's the time flipped version of h. That's our weights. Okay. So you can think of this as some sort of smoothing of that input x. All right. I happen to choose an h that was sort of causal. In fact, like calculating the output value at any given point in time only required looking at the past inputs. Okay, so I chose h that way just to make an interesting example. So if x was actually being sensed in real time and you only actually had the output, you only actually had x available to you up to the current point in time, and you needed to give an output, then you would be restricted to use a weighting function that only used the past. And this h happens to be such a function. Okay. So convolution is actually linear if you, for a fixed h. So in other words, if we look at x of t or x of n comes into something that does convolution, this convolution box that does a convolution with h of n, then this, and then something comes out, we'll call it y of n. Okay? This is a linear process. What that means is if we put in a x of n, or a x1 of n plus x2 of n, and we convolve that whole thing with h of n, then by linearity we should get, we should just get a times the convolution of x1n with h plus the convolution of x2n with h. That's what it means to be linear. And this is in fact true. And to check it, you simply plug this into the convolution formula. In fact, we can do it right now. This here, that equals sum over k of ax1k plus x2k h of n minus k. And everything's nice and linear here. We can separate that into two sums. Whoops. Which equals the right-hand side. Okay. All right. So it's a linear operation. So now let's look at another way to think about convolution. Are there any questions so far? I've given a definition, done an example. I'm assuming most of you have not used convolution before. How many of you have before today's lecture? Okay. Maybe some people have seen it. In fact, you've all done it without knowing it. Let me point out why. Polynomial multiplication is convolution. All right, so let's see what we mean. Suppose you have something like, you have like a, let's say, a0 plus a1 z plus a2 z squared. Okay, some polynomial. I'm just thinking of actual numbers. I won't use symbols there. I'll use numbers. So you got like 1 minus 2z plus z squared. Okay, and you multiply that by 5 plus 4z. Okay, and you know you do all these cross multiplies, but if you think of these, if you represent a polynomial just as a vector, so you can think of these each polynomial is represented as a vector. You've got one that's just 1, comma, negative 2, 1. That's the first polynomial. And the second one is 5, comma, 4. And if we interpret these correctly, that can be a representation for a polynomial. Okay? And it turns out that when you do this multiplication, it's exactly the same as doing a convolution of these two vectors padded by zeros. Why is that? Well, because I could just do the following. I could say, how do I calculate all of the outputs that are... okay, what if I write this one? So to calculate all the outputs, I have to do all cross multiplies, but I'm going to do it in a certain order. I'm going to put 5 here, 4z here. Okay? I'm going to multiply the terms that are straight above them. So 1 times 5, and 0, this is 0z inverse. Okay? And if I do this multiply, I get all of the terms that have no z on them. Okay? And then I can do this multiply, 4z plus 5 this way, and I can multiply, let me get rid of all the parentheses here. Okay, multiply these terms to get all of the z output coefficients, right? And so forth. What have I done? A flip and a shift to calculate the resulting polynomial. Okay, so in fact, now we're doing, of course, the only difference between this and what we've already done is that we're interpreting a finite length vector here as a part of a, so far we've talked about convolution on signals that go from negative infinity to infinity, and yet I'm talking about finite length vectors. But just be kind and don't complain about that. And we have this convolution equals whatever the result of that is. I don't want to calculate it right now. Okay, equals resulting polynomial. Okay, so you've seen convolution, but not described as a signal processing tool before. All right. Now, let me introduce a useful discrete time function. I'm going to introduce two. First of all, let's have what we call the Kronecker delta function. It's the simplest function that you can think of. Delta of n just equals 1 if n equals 0. Okay, so it's just this thing here. That's the delta function. All right, very simple. Notice that a lot of these nice functions that we're introducing, like we did for continuous time, the rect function, things like that, a lot of these are actually indicator functions. In your first problem set, we defined an indicator function that's 1 on a certain set, 0 elsewhere. These are all just particular indicator functions. This is the indicator function that the argument is 0. Okay, how about the unit step function? We have this in continuous time, and I just want to emphasize one thing about it. We'll use the same notation here. U of n equals 1 if n is greater than or equal to 0, 0 else. One thing I want to emphasize is for discrete time functions, we care about each point. So u of 0 equals 1, that's important. Okay? In discrete time, every value is important because all you have is a sequence of numbers. In continuous time, we don't care about any particular one value because you actually have, the range is continuous and any one value is essentially meaningless. Okay? But in discrete time, each value is important. So it's not arbitrary. It's, we define this to be 1 at n equals 0, and that has to be done that way, or you'll get different answers. Whereas in continuous time, if you redefined what the step function was at 0, you'd get the same answer for anything involving a convolution, a Fourier transform, or whatever. It wouldn't matter in continuous time. Okay. So these delta functions, let's look at this delta function property. And there's something that we call sifting. And all it means is that if you sum over all n, some function of n, I'll use x because we usually are talking about signals as our functions of n, some function of n times a delta function of n, then that equals just x at 0. Right? That's pretty clear because delta is 0 everywhere else in that sum. Okay, let me state a slight generalization of this, one that you'll usually find a little more useful, and that is that if you sum n equals negative infinity to infinity of xn delta, a shifted delta, n minus something, let's say cap n. Okay, that's just going to be the value of x at cap n. Because the shifted delta is just a 1 at cap n. That's all it is, right? In fact, an even simpler way of stating this is not even in the sum. You could just say xn delta n minus cap n. What you can do is you can replace everything that's multiplied by a delta. You're free to replace the argument little n with the other argument big N. So this equals x of big N delta n minus n. So that's often a nice simplification. Of course, you can see that using that simplification, these sums become trivial because now the x cap n just comes out of the sum. So if you sum both sides over little n, well, this side, the right side is easier to sum. The x cap n just comes out. And all you're doing is saying, what's the sum of a delta function? It doesn't matter how much you shift a delta function. When you sum it, you get 1. Okay, so there we go. There's a sifting property. In fact, there's another way to interpret this that I kind of like. Interpret a signal as composed of delta functions. Okay, to show what I mean, I'm going to go back up to our x of n that we defined for this example way at the beginning. So x of n here, we could have said, we could define this. In the past, I defined functions using an open bracket and say, here's the value at this point, here's the value at that point. It's a bit tedious, but here's another way to define this using the delta function. We just say this is delta of k. Actually, let me go up to n here. Okay, this here is delta of n plus 2 delta of n minus 1 plus 3 delta of n minus 2. That is that function. That accounts for all non-zero values of x. Okay? So I can always represent a signal as a sum of delta functions, each with their own shift and with the right coefficient. The coefficient being exactly the value the function takes. Now, for short signals that were mostly 0, that's a very convenient way to do it. But for signals that go on, it's going to be a big formula. I'm basically writing every value of x as a coefficient of a delta function. Okay? But notice that's exactly what sifting is saying. So let's go back down here. And notice that I'm saying that x of n, if I just rewrite this above with new variables, notice that this equals sum over k. I'm just changing my variables because above I sum over n. X of k delta of n minus k. So by sifting property, this, of course, is true. You just apply it. You get that this is equal. But notice that now we have an interpretation where xn can always be written as a sum of delta functions, each with a certain shift, and where the value of x is the coefficient of that delta function. It's exactly the decomposition I just did as an example. Okay, so many ways to think about this. Great, because next, what I want to do is show you that we've already learned what convolution with a delta function is. So let's write this out formally. Whoops, convolution. Okay, so suppose we want to look at delta of n time convolved with some arbitrary thing, which we'll keep using h as our function we're convolving with. I want to know what is the answer to a delta function convolved with some h? Any guesses? Well, I will show you. What was that? Yes, it's going to just be the signal. Exactly. What I'd like to do is, okay, fine. I'll do it this way. Well, let me switch these around for now. Let's say h of n convolved with a delta function is going to be, by definition, sum over k, h of k delta of n minus k. Now we use sifting property to say that this equals h of n. So it's exactly what you said. So delta function is like the identity function for convolution. Okay, does not change the signal. There's one other thing I want to show, that convolution is symmetric that way. Okay, is let's say commutes, or yeah, we'll say commutes. So x of n, an arbitrary x of n convolved with h of n equals h of n convolved with x of n. Okay, let's check this. To check that, we just plug in the formula. All right. So that equals sum over k, x of k, h of n minus k. And what we can do is just change variables and let m equal n minus k. Now, since we're summing k for sum, the order of the limits of the sum don't matter. So we have k. We have now sum over m of x, and we would replace that with n minus m h of m. And that, of course, switch these around here, and you'll see that's exactly the convolution of, that's exactly this above formula. Okay, so convolution commutes, all right, which means we could have written this in the way I wanted to actually write it, that delta n convolved with h of n equals h of n. Okay, same thing. Now, that gives us a new way to think about convolution in general, because what we can do is think of okay, suppose we want to do the same convolution as above. We had x of n equaled 1, 2, 3, and then zeros, right? That was the signal we convolved in our example. But we're going to represent this now as delta n plus 2 delta n minus 1 plus 3 delta n minus 2. Okay, now we had our h. there's one thing I want you to know first. Now we want to calculate an x of n convolved with h of n. And in a case where x has only a few non-zero values, there's actually an easier way than the flip and shift method. Okay, and that is to realize that this equals, by linearity, it equals delta of n convolved with h of n plus 2 delta n minus 1 convolved with h of n plus 3 delta n minus 2 convolved with h of n. So if I can do each of those easily, then I can do the whole convolution very easily. The first one we already know. We know that this equals just h of n, that first term, right? But how do we do these convolutions? A shifted delta with an h. So that actually is a property that if I had more time, we'd derive. But convolution has a property which I think we'll come back to it in another lecture and talk about it a little more. It's a very important one. Convolution, it's not only linear, it's time invariant. And what that means is if you shift one of them in time, like here we've shifted the delta input in time. Then the output is just the same as, is just a shifted output. So this becomes plus 2 h of n minus 1. And this becomes plus 3 h of n minus 2. So like I said, we'll revisit this time invariance notion. Just trust me for now that when you have a delayed delta function convolved with h, you get a delayed h. Okay? Well, that was easy. Now we just have to add up these three h's. Remember what h was in our example above? It was h, so we had 1, 2, 2, 2, 1. Right, that was h. So then we'll get the same type of thing for h of n minus 1. Well, 2h of n minus 1 will be two, 4, 4, 4, 2. All right, so that's 2h of n minus 1. And similarly, 3h of n minus 2 will be 3, 6, 6, 6, 3. Okay? And then we just add these three things up. And believe me that if you add these up, you're going to get exactly, you can probably even see it in your mind, you're going to get this thing when you add those up. Okay? So this actually gives another intuitive way to think about convolution. All right? Even a different way to compute convolution, but only if one of your signals is mostly 0. That's the only time you would actually compute it this way. Otherwise, it's not going to be easier. It'll be easier to do the flip and shift. Okay, but it's always a good way maybe to think about what convolution is doing. Okay, I want to talk about to revisit, we talked about signal manipulation when we were talking about the Fourier transform last time, and we did both a time shift and a time scale, but we didn't really look at doing both together. Now I know that you can figure this out on your own if you want, but it's worth, because it's a common point of confusion, it's worth talking about a little bit. Okay, so if we have x of t, let's say, is this signal. Here's t. Okay, some simple signal like this, 0 everywhere else. And you then want to look at something like x of minus 2t minus 4. You want to say, what is this new signal? Okay, there's both a time scaling going on there with a -2 coefficient, and there's a time shift, the -4. One of them has to be done first because, and depending on which one you do first, you could get a different answer. So there's a correct way and a wrong way to do this. The correct way is the following. You can start with x of t, and you could do two different steps to it. You first shift by 4. So shift right by 4. That's what the -4 does. And then, so that's step 1. Step 2 is scale by -2. I mean the time axis by -2. Okay? So why do it in this order? Because if you look at the formula, you might say, well, gosh, I usually do a multiply before an add if you look at order of operation. All right? So doesn't this seem backwards? And just remember that as a way to remember, if you're doing this right, you actually do outside first. So you do it kind of in the opposite order of what, the way you would compute the argument. There's a simple reason for this. So let's look at what that means. So step 1, I'm going to shift by 4. So I'm going to get 4, 5. So there's the shift by 4. Okay. Step 2, I'm going to take this signal, and I'm going to do a multiply by a -2, which means you shrink the time axis. So when you multiply by a -2, you bring things inward. So you are going to end up with -2 to -2.5. That type of thing. So that's the final result. Okay, so that is x of -2t minus 4. Okay, so that means, why did I do these steps? Well, because this here is x of t minus 4, right? And if it's confusing why we did this in this order, I find it useful to give a new name to this function. Just call that z. Z of t is x of t minus 4. What does that make this? That makes this z of -2t. Okay, so what I've done here, now I've split the two steps using a new variable name. For me, that just avoids some of the confusion, because it's clear that this should be x of t minus 4. I've just shifted x of t by 4. Okay, if I call that z of t, then z of -2t should be just now to do the time scale. Okay, and can I check that these two are in fact equal? Yes, because z of -2t should be whatever z of t was defined as, with t replaced by -2t. Okay, so you see that if you put a -2t in here, you get what we wanted. Okay, so that helps you realize why we do things sort of in reverse order. If you had done it the wrong way, if you had done a time scale first and then a shift, this you could see, there's a number of ways you could see why it's wrong. You could try to write out the way I did here and use what we know what it means to plug in -2t as the argument. It means you just go swap -2t for t. And you would see that it doesn't work if you do it the other way. Another way to check yourself is just plug in some values of t, right? I mean, we think that this is right. Well, what if we let t equal -2? Well, we're going to get 4 minus 4, 0. We should get x of 0, and we do. This corresponds to t equals 0 in our original signal. Let's plug in -2.5. Plug that in here, we get x of 1, and yes, those 2 points correspond. So we've done it correctly. If you've done it incorrectly, that you'll see easily by plugging in a few values of t that you've done it wrong. Okay. Now, what does this mean? Oh, let me say one thing. There is an alternative way to do this same thing. You could do it in the other order. You could do scale first, then shift, but but the scaling and shifting would be different. We'd have to write, notice x of -2t minus 4 equals, I could do a factoring here, x of -2 t plus 1, right? Plus 2, yes. Now, this would imply that you first do the time scale by -2, then you do a shift to the left by 2. And notice that would work as well. If we do the time scale of this by -2, we'll get 0 to -½ The triangle would be backwards. All right. Then if we do a shift left by 2, we'll get to the correct final result. So this is fine. You can do it in the other order as long as you've correctly updated the numbers that you're doing the shifts and flips by. I want to connect this to the Fourier transform as the last thing, just to say we might want to know what is the Fourier transform of x of -2t minus 4 from a starting point that suppose we're given the Fourier transform of x. Then we'll just say that is capital X of f. Then we can use the rules we learned about the Fourier transform and say, well, that means that we've done two things to this signal. We should apply the two rules. It means that the Fourier transform of x of t minus 4, remember, notice I'm doing this in the proper order. I do the time shift first. Again, if I use the rules in the wrong order, I'll get the wrong answer. So at the time shift first, we have a property for time shifts. That's e to the -I 2 pi f, and then it's a shift by 4, so it's 4f, right? X of f. Okay, and then we would say that the Fourier transform of x of -2t minus 4, now I've applied a scaling rule. So that's going to be 1/2. And then I replace every f with an f over 2. That's what the rule is. Or f over -2. Okay, so that means it's 1/2 e to the -I 2 pi 4. And then I'm going to have an f over -2. And here I also have to put an f over -2. Okay, so if I wanted to simplify, it's 1/2 e to the I pi f. Correct? Yeah. Nope. E to the I 4 pi f. F x of f over -2. So you see I was able to use two rules together. Again, I could do this alternate way. I could do my time scale first and then a shift, as long as I switch the shift to be a +2 rather than a -4. And you can, as an exercise if you want, just do the Fourier transform properties and show that you get the same thing if you do it in the other order properly. Okay? All right. Thanks.